Thank you for invitation. So the subject is about, I think, combines three different branches of mathematics. One is just algebraic geometry with algebraic group actions. And then I would compute some characteristic classes of orbits of a, in fact, the Borel group, the characteristic classes of orbits acting on some natural space. And everything is encoded in some nice combinatorics that you partially know from the knowledge about just flag varieties, where everything is governed by permutations. And I will extend this description. And the characteristic classes I want to compute are elliptic characteristic classes. So to define these elliptic characteristic classes, I would need some knowledge about elliptic curves and bundles over elliptic curves or products of elliptic curves. So there are a mixture of many things. I would be happy to give a blackboard talk, but there are many pictures, and I'm not very quick in drawing and writing, so I made very few slides, and some things I would explain on the board, on the green board, if it's necessary. Okay, so, and I should say, so this is everything somehow not started, but the first input was from my collaboration with Richard Rimani and Laci Fecher. So here we studied motivic chain classes for the group actions. I mean, the motivic chain classes for the orbits in some spaces like Grassmannians or like flag varieties, or also matrices with the Borel group action. And then it went two directions. One was with Richard Rimani, it was elliptic classes, but only for the homogeneous spaces like B over G and then B over parabolic subgroup. I mean, G over B, G over parabolic. And other direction I did with my student, with Piotr Dnitsky. And it was about only motivic chain classes. So it was motivic chain classes. This was only for motivic chain classes, but for the more general things called, I mean, what is in the title? Orbits of the Borel group acting on the matrices satisfying that square is equal 0. And so this is somehow outcome, push out of this diagram. So this is elliptic classes for space of matrices satisfying square equals 0. And also I should mention my students, Jakub Kącki, with whom we did a version of motivic chain classes, but which is between motivic chain classes and elliptic classes. So this is about other concepts. So somehow this talk gathers all the information, but basically I would talk only about elliptic classes. But to tell you about elliptic classes, I would just go through something very basic, like fundamental class. But let me start with combinatorics. So you have permutations. So you have one set red drops and other black drops. There's bijection. There's order between them. And I have map from one to another bijection, which probably does not preserve the order. So these are permutations. Other combinatorial objects, a partial permutation. So you have map, which is not everywhere defined and is not surjective, but is injective on the domain. third kind of combinatorial object is a directed link patterns, which was in literature rather called link patterns, but I need other one. So this will be called directed. So you have arrows that here you have domain and the target. Here I do not care what is domain, what is target. I have just some arcs, and the rule is, maybe I could write the formula, but it's pointless. If you have a dot, so it can be either a source or a target, or do not participate. So three possibilities. And arrows always go west. And finally, link patterns. These are things that you can go anywhere. Okay, so this is combinatorics, and this combinatorics is related to geometry. As you know, if you take permutation, this is a Weil group of GLN or SLN. And if you take a flag variety, GLN divided by Borel, I mean the upper triangular matrices. So that's why this direction is chosen. So the orbits of the Borel group on the flag variety, this is the same as action of Borel times Borel on GLN. You act from the left and from the right. One normally, other by inverse. So these are classical Schubert varieties are just described by combinatorics of the permutation group. The next object, these partial permutations, are the described matrix Schubert varieties. So GLN are the matrices that are invertible, as you know. And there are more matrices which are not invertible. So this is GLN, or just endomorphism of CN, and you have actions from the left, from the right. For example, you have zero matrix, which is orbit by itself, but are other orbits. I will quote in the moment the name. So here, this is a Brouillard decomposition. Here's then another name, very classical thing, but maybe no one recalls it. Still, this B times B orbits acting on GLN, on the matrices, are, the theorem is that every matrix, every orbit of a matrix contains an element which is just defined on the basis, and some vectors are transported to other vectors of the basis, and some are just forgotten. Okay, and finally, you have, this is something different, because I take twice big matrices, 2n by 2n, and I act by the Borel by conjugation. And this is a kind of trick that people maybe from representation theory notice that if you have a matrix and A, you can associate a doubled matrix, 0, 0, 0, A. So this is of dimension n, this is of dimension 2n. And acting here B by B, maybe I say Borel of dimension n, one from left, other from the right, and you look at the orbit, this is the same as acting by the big matrix, upper triangular. So here you have B, here you have B prime, and here whatever. So the orbits with respect to this product are the same as the orbits with respect to this matrix, but acting by conjugation. You can conjugate by this matrix. So if you conjugate this block, so you multiply by B from one side and from the B prime inverse. So talking about orbits, this is equal UL. Either I take square matrices and act the product of Borel's, or I take twice big matrices and act by conjugation. And those who are upper triangular correspond to this, but there are others. And finally, and here is remark that this is upper triangular. And upper triangular, you can forget about upper triangularity, and you have just linking patterns that matrices that are whatever. And this matrix has so maybe call it embedding of A. So this embedding of A has a property that squared is equal to 0. So instead of upper triangular block upper triangularity, you just impose the matrix has square 0. Okay, maybe I give more examples. Or maybe theorem. So theorem is the following: that if you consider matrices two nilpotent, that is square equals 0, and orbits with respect to Borel group, by acting by conjugation, then in each orbit you can find a matrix that contains 0 and 1s, and this is unique if you demand that this matrix corresponds to a pattern. Maybe this is pointless to give a precise definition, but this pattern means that 7 goes to 4, so this is 7th column goes to the 4th vector, and 6th vector goes to the 2nd. All the rest goes to 0, and this 4 vector and 2nd vector also goes to 0. So this is the geometry of the action of the Borel group on two nilpotent matrices is just encoded by such a diagrams. And this is particularity of the case of two nilpotent matrices. If you take 3 nilpotent matrices, you can ask about A to the third equals 0. Then there are infinitely many matrices, I think, starting from dimension 6. So this would be not the decomposition into Borel orbits. One would have to take more general, because we want to have space decomposed in finitely some stratification or some just paving by something easy. And then maybe you should take a Białęcki-Birula cells that is awesome. You should choose some discrete invariants. And the first theorem about decomposition of GLN, this is classical Brouwer decomposition. If you want to decompose all the matrices, not necessarily invertible, there's something like Renner decomposition. I just learned this from my algebraic colleagues, so I didn't know. Now the matrices which are upper triangular and their square is 0. So this is work of Anna Melnikov, very elementary paper, just few pages. And finally, all matrices satisfying square equals 0, that they contain, they are indexed by such a thing. For example, one can find it in the paper of Booth, Reinecke. These are people from representation theory, representation of quivers. Because action of the Borel group can be representations, as a representation space can be changed. Instead Borel group, you can take chain of GLNs and move to some quiver with relations, and there are people working on that. But still, the theorem is elementary. One can try to give it to students on the first year of mathematics. Just find the conjugation, find a good basis. You do not talk about conjugation. You just ask, find a good basis that the map is simple as possible. But it is not so elementary. I tried. Okay, and these orbits, this is some structure. So I take A square equals 0 in 4 matrices. Oh, it should be endomorphism C4. This is a typo. Square equals 0 and rank equal 2. So in general, this condition square equals 0 and rank equal 2, this is just one conjugation class of the GLN. But this is the things that are Jordan form block, 2 blocks 2 by 2. But with respect to the Borel group, you have interesting structure. Everything has a symplectic structure as any conjoint orbit. And the minimal orbit, this is just matrices that are concentrated in the northeast angle, just here. So the condition of being rank 2 is that is not equal 0. This is not equal 0. But if I take a closure, this is just a vector space, 3-dimensional vector space. So this is easy. 3-dimensional vector space with easy divisor describing the boundary, just coordinates being 0. This is the condition. And then you can, for example, here, if you switch 2 with 3, you obtain such a diagram, such a pattern. And if you change 1 and 2, you obtain that one. But also you can change 3 and 4, and you obtain the same. Except that if you have labels on the arcs, the labels would differ. Because once, if you change 1 with 2, then the first label will be inside. Otherwise, if you change 3 and 4, then the first label will be the outside. Okay, and this is the picture, how these patterns are changed with respect to action of the elementary reflections of the symmetric group. Yes, yes, I said C4. C4, it's C4. This is my typo. Yes, I will correct it. Yes, and this is illustration of the action. You can draw it like you draw braids, except that this is no, I mean, like you illustrate permutations. This is first transposition. If you switch this one, you get such a picture, or, okay, and this is result. This is the minimal orbit. The closure of the minimal orbit, there are no condition of these black dots. And applying this relation, you obtain such a space of 2 by 2 matrices, but in the northeast corner. But if you apply this one, no, this one, so you have possibly 5 non-zero elements, but the condition that this is square is equal 0, it's quadratic. So this is a quadratic cone times the parameter c. So you see here that this closure of orbits are not smooth in general. Okay. And what is geometry behind this permutation action? So these are standard minimal parabolic group. You just, to the Borel group, you add one reflection. So you have this upper triangular matrix plus one entry. And for an orbit, suppose A is this 0, 1 matrix. You conjugate this matrix, dot means conjugation. You conjugate this matrix, you obtain another 0, 1 matrix and take a closure. And this is the same as action with this parabolic group and spreading this previous orbit using parabolic group. And there is a morphism from the twisted product. So X, suppose X in the beginning was smooth. If you create this twisted product, you again get something smooth. And you have also fibration. X is a fiber. This is twisted product, and this maps to a P1. So this is fibration over P1. And iterating this, you obtain something like Bott-Samuelson resolution, starting with the minimal orbit. If you remember the Bott-Samuelson resolution for the Schubert varieties, you start from the point and create this tower. And here you start not from the point, but you start from the minimal orbit, which if you divide by the Borel, you go to the just to the point. And okay, so I should give some name. So it follows from the Brion work on spherical varieties, and in that form it was written by Bender and Perrin. There's quite recent paper. I mean, it appeared, I think, 2 or 3 years ago. The preprint was earlier, but this is for any semi-simple group, you can do the same. Except that for other semi-simple group, this x-min might be already singular. So in type C, already this minimal, the starting point is singular. But having resolution of this minimal, you can create further resolution of further steps. Okay, so this is the geometry behind it. And we want to compute some characteristic classes. I mean, maybe not everybody, but people with whom I deal, they are interested not in the varieties itself, but the invariants. And where does this live? So these orbits live in the vector space. So topologically it's contractible, but it has a group action. Okay, so let's see. Okay. So Borel group, of course, acts on this space of endomorphism. So my previous to n is now m. M doesn't have to be even. Now we forget about our source that were just Schubert varieties. We just take endomorphism. The matrices with square equals 0. Their orbits, and then closure. This is for sure, this is invariant with respect to the Borel. And also, since these orbits are nilpotent, so they are conical. So they're also invariant with respect to a scalar multiplication. So in fact, you have bigger action of torus from Borel and other action just a scalar. Or if you want, you can projectivize, so you lose this scalar action, but the situation is more rich. So you have equivariant variables in equivariant cohomology. This space is contractible, so it could be just a point if you wish. So equivariant variables of the maximal torus plus extra variable corresponding to the scalar multiplication. So you can say that a characteristic class, for example, fundamental class of such an orbit closure, is a polynomial in these variables. And it's homogeneous, it's of degree exactly equal to the codimension. And there are better invariants, which I will not have time to tell. These are Chern-Schwarz-McPherson classes. These are, you can say, deformation of a fundamental class. These are homogeneous. These are not homogeneous, but better behave with respect to morphisms. And eventually you can go to case theory. And in case theory, you have fundamental classes. And there are subtleties about fundamental classes that you have choose one of the notions of fundamental class in case theory. This is not the O class of OX. It's something different, that you take a resolution and you push forward. So if there are, so this is a problem here for Schubert varieties. Everything is easy, and these orbits, the closure, the singularities are not known. I think it is not known. They are Cohen-Macaulay. It causes problem with the notion of the fundamental class. But in some sense, I do not care, because I have this resolution, and in fact, I would push forward something from a resolution. So somehow I just, okay, and you have motivic Chern classes. These are lives in K-theory plus one parameter. I think I will not tell you what are motivic chain classes, except that in the compact case, this is something that computes chi-Y genes. If you integrate motivic chain class, you obtain chi-Y genes. Okay. And now the classical part, I will just stick to the fundamental class, and then I will say that everything generalizes very well to other types, and I will just concentrate on elliptic classes, which is new. But for fundamental classes, if you have polynomial in n or m variables, and maybe other parameters as well, you have a divided difference operator. You just take a polynomial, subtract the same polynomial with switched variables, I with the next one, and divide by this difference. So in short, this is f minus SIF divided by the difference. This is divisible. This is exercise for even for the below university. Okay, and in the Schubert calculus, that's this divided difference compute from one Schubert class of the one Schubert cell to the other Schubert classes. This is these operators were defined by Bernstein, Gelfand. And here, because of some convention, some order, if I took lower triangular, it would be better, but from other reasons, I take upper triangular Borel group, so I have some sign. So don't worry about the sign. So if you have some class of the orbit, and this action of the one transposition, if it enlarges the orbit, so its codimension drops by one, complete codimension drops by one, then you having a fundamental class of X, you can apply this divided difference operator and you get the next class. Okay, and here algebra appears. This divided difference operator commute if the indices are distant and satisfied braid relation. But this is not representation of the symmetric group, but square is equal 0. And it's called, I think, called Nil-Hecke algebra or some version. Okay. And similar operators you have for the computing Chern-Schwarz-Macpherson classes, fundamental classes in K-theory. But let me concentrate on the Mazur-Lusztig operator. You just add one variable, y, and Lusztig defined such operator. X's were standing for the Chern classes of the tautological bundles on the flag. It was for general G, not necessarily SLN or GLN. And we had such operator, and Lusztig showed that this operator acting on the cohomology of the K-theory, also equivariant K-theory of G over B. Here G is GLN, because you have this braid relation just corresponding to simple laced group. You have, and the quadratic relation can be written that way. And it turns out that this operator acting on the functions also preserves this relation. So K-theory is a quotient, some polynomial, some low-round polynomials, but these relations hold on the level of functions. And also we can show that recursion of the motivic Chern classes satisfies the same stuff like a fundamental class. If you have motivic Chern class, whatever it is, and its operation enlarges the orbit, then this formula is satisfied. And if you don't know what are motivic chain class, you can define motivic chain class in that way, that you suppose you know what is the starting point, and you have braid relation. So you have motivic chain class for Schubert varieties, or also for these linking patterns. Okay. And maybe the general pattern. These operators look like something I will explain in a moment. Relative chain class divided by Euler times f, and this depends on the parameter xi plus 1 minus xi, and Chern divided by Euler divided by the opposite difference, but multiplied by the transposed parameters in Si. Or maybe I don't need. So I just explain from where you have it, because you have P1 here, and you have this space resolving orbit. So this is Pi times Bx, and it projects to P1, which is Pi divided by B, and it's okay, and you have x here and x here. And for example, suppose that this point corresponds to identity and this to Si. And somewhere there's 0. And the 0 is, and this is contained in endomorphism of. So if I compute, if I use localization theorem for the either for cohomology or for the equivariant case theory, so I have to sum up over these points. At one point, you have vertical direction, that's some cohomology class here, and I have normal direction. So if I, from this cell, if I build new cell, and I mean the open cell, so there are two contributions of normal direction. Here you have just chain class of the normal direction, and here this is chain class minus this one, minus Euler class. So this is short explanation for this formula, and you have here exactly in the easy world. This is computing just Chern-Schwarz-McPherson class. You have two factors. Here factor, you take just Chern class divided by the Euler class. And this relative, you take Chern class divided by Euler class minus 1. It happens that it's 1 over x somehow. And then the same here for the case theory. And for the elliptic cohomology, you have this expression, which I will motivate why you take it in a moment. Elliptic theory is you can think about elliptic classes. There are classes, you can look at them that they live just in the usual cohomology, but you switch the notion of the Euler class. Here Euler class was X. Here's in fact the Chern character of the Euler class in case theory. And here you take theta function, which would be in the next slide. And so this computation would involve theta function. Okay, and maybe I switch the slide. Also, I use normalization. I want to have it homogeneous, so it was 1. Instead of 1, I plug in h. And this part does not change. Also, here was y, and now I say that y is minus e to minus h, and now it looks nicer. It looks like this. You have function of x plus h divided by two things that in the separated variables in the denominator, And in the elliptic case, you have to normalize because you want to have that, I mean, some normalization. And this genus was considered by Hirzebruch. In the singular case, this is theory of Borisov and Libgober, that they realized that for the singular varieties, you can, where you have divisor at the boundary, the procedure is that you resolve, and you have to control what's happening on the boundary divisor of the resolution. And unfortunately, you have to take into account canonical divisor, so you have to know some geometry of the space downstairs. There are some constraints. For example, canonical divisor minus boundary should be Q Cartier, so even that you can pull back it to the resolution. So there are some constraints, but we don't care for the moment. Just look at this formula. It's not possible to avoid parameter. You should plug in some parameter. So what parameter you plug? Let's call it mu. And this parameter would depend on the geometry. Okay, so I should say just briefly what is theta function. Theta function, okay, so this is the definition. You don't have to remember it. Just remember that it depends on the parameter tau. Tau is from the upper half plane, so it parameterizes elliptic curves, and usually Q is the exponential of tau. And you have this function depending on tau, so depending on the elliptic curve with this periodicity condition. And my function was a combination of theta functions, so this is the combination. And in fact, this function descends to a, so this one does not descend to C star. It's E to this one, but you have sinus sign of p pi, not to p pi, so it changes sign when you add one. But if you look at this function, this minuses cancel. So anyway, we prefer to write formulas not using theta function, but using the delta function. And this delta function was considered by Don Zagier long time ago. Also appears in Libgober paper on. Anyway, this delta is important. Okay, and you look at the theta function as a function. Okay, it's a function on C, but has some periodicity. So it defines a section of some bundle. This bundle is C times C. You divide the C by a lattice. Here you just divide by lattice. And here you have this sophisticated transition. But you can say that Jacobi theta function is something really God-given. Is a function, is a section of a bundle, and the bundle is given by a divisor 0. So what can else be more natural? Maybe trivial bundle, but trivial bundle does not have many sections. Okay, so you have, and we can extend it. So by Mumford, I think there are lectures on that, but the bundles over the product of elliptic curves are determined up to transition by quadratic form. These are some transition of the functions. So if you have a combination of theta functions, so depending on different variables, you can think of it as a section of some linear bundle over product of elliptic curves. If you have just one product of things, the problem is with addition. You cannot add sections from the different bundles. Of course you can, but it does not, as a functions, it's still the meromorphic functions, but they have no good transition. They do not define a section. That's why we care about functions that they have the same transition properties. For example, this delta function has this transition properties. So this was determined by a matrix, but instead of matrix, I write quadratic form. theta has this quadratic form. So this, if you make a calculation, is xy. So you still see that this is a very fundamental thing. Okay, and I define elliptic operators like this. You have parameter, you have this relative part and something like a term part. Here you have h, and then some parameter mu. And you can think that it acts on the function on Cn, these are x's, plus h, and some other parameters that are mu. And this theorem, I mean, it was already noticed by, I think, in our paper with Richard, but we didn't write it in that way, that we have these relations. This is Braid's relation, but with parameter. Braid relation with dynamical parameter. Also, you can say this is Young-Baxter equation. You can rephrase it. And also you have a square. Square, if you have mu, to obtain something of the good type, you are allowed to compose with the parameter with minus mu, and then you get a function that is just depending on h and mu, does not depend on the variables x. So if you wish, you can normalize all the operator that the square, but square meaning that you have opposite parameters, that you have identity. Okay, so we have 4 minutes. The conclusion is that I define these operators and I define action. I have pattern, I have minimal pattern. I did not write it and I will not. I start with some minimal function, which is pure in the sense that it defines some section of a bundle. And then I apply these operators. And what operators I'm allowed to apply? I want to preserve this purity, this quadratic form. So, okay, so this is operator again. But if we want that this is pure, then mu is determined uniquely. See, so suppose this has quadratic form Q, and this expression is the difference times mu. And also here, we transpose parameters in Q and add this form. If you make some easy calculation, you see that mu is just a divided difference shifted by h. So the conclusion is that the action on the types just coincides with permutations. But you have to shift the origin, shift by some quadratic form, which is exactly the sum of the positive roots multiplied by parameter h. So this is calculation that one can do. So this is somehow connection to the classical theorems about Weil character formula. This action appears. And this is the last slide. So we have parameters, and what we can do, we can switch these things. And in our setup, we have to associate variables to arcs, because the elliptic class depends on some parameters associated to boundary. If you start with the matrix of some rank R, so you have R parameters. Because this is this upper triangular, you have at each entry here, you have parameter corresponding to arcs. And if you switch these arcs, you can compute what is parameter mu in this Hecke operator. And if you switch A with B, you have to take this mu. On the other, if you switch targets, this is opposite. Also, you can do this thing. And also, if you have empty dots, you can just move source or target, for example, here. So this mu would depend on A and also on H with some multiple. And you count this multiple, you just count how many empty dots. Here's empty, here's empty, Here, maybe I didn't draw, and this one last is empty. So you take mu such a. Okay, so this was last slide. Maybe I just write a key. Okay, so the two formulas that I used, one is square. That square is identity up to some particular multiple. Other is the braid identity, braid relation with parameters. And also maybe here, if you start with minimal, and if you apply one switch, so suppose alpha, beta, and if I apply C1, and here maybe I plug in my favorite, or maybe my favorite, so I preserve purity, C1. So I switch this one, and I get, so beta is here, and here is alpha. Or I can apply the other switch, alpha, beta. If I switch this one, C3. So now I C3, so I would have alpha here, beta here. So as patterns, they are different, but as a labeled pattern, they are not. So I would have certainly different classes. So if I take elliptic classes of a X minimal, and in this range, and apply C1, this with pure, and C3 with elliptic class X. So they are equal, but I have to switch. Maybe I call this S. I have to transpose alpha with beta. So this is the third relation that I need in my calculus. And having only these three relations, I mean square, braid, and this relation that correspond to so-called four-term relation in the paper of Richard with Tarasov and Varchenko, I can prove that everything is well-defined. So for these pictures, I have a well-defined characteristic class, elliptic class, and also using Borisov Libgober theory, I can give a topological definition of this class, which I do not do because it's too much. Yes, and I finished, I think 3 minutes extended. Yes. This is easy because, okay, this is minimal. So this is M and this is R. And the entries of the matrix, you have to look, maybe I neglect this parameter U, which is missing in here, but just look. This entry in this matrix has a xi acts here, and then you have J. So you have to take a delta of xi minus xj h. So these are inner things inner things that are, and this is a product. I will not write formula, product over this inner dots. And also you have these dots. So this product of delta xi minus xj. So this is I, and maybe I call it this alpha I. Alpha I corresponds to this entries. So this is I start with such a simple thing that if I started with, okay, and I should say this this specializes to a fundamental class and to Chern-Schwarz-McPherson class, and it agrees with this computation that what is the Chern class. So this is a product. So this is just a product of C to some power times C star some power. I will not refraction. So such a thing is easy. You have to know what is the characteristic class of C and C star with action, and you take a product. Thank you.